We now start to introduce the most important research approach in the last 2 or 3 years. Okay, that is deep learning. Okay, in the following, we will use the slides provided by Professor Hongyi Li at National Taiwan University. Okay, so because Professor Lee's slides are very appropriate, very easy to understand, and very appropriate to be the introduction material of deep learning. So we use we use his slides. So you have already known the deep learning, the terminology of deep learning. Okay, and deep learning attracts lots of attention in the recent 3 or 4 years, starting from year 2012. Okay, so I believe you have seen lots of exciting results before. And this figure shows the growing use of deep learning at Google. So we can see that at the beginning of year 2012, almost no project used deep learning. But starting from the end of year 2012, the deep learning has been adopted to many projects. Okay, including many products like Android apps, drug discovery, Gmail, image understanding, and so on. Okay, and this is just the situation at Google. And for the worldwide, we believe that this situation happens everywhere. Okay, in many companies as well as in the research community. So before introducing the detail of deep learning, we first introduce the concept of machine learning. Okay, so we can think that machine learning is a process that we want to look for a function. Okay, what kinds of function? For speech recognition, this function may take an audio signal as input and output the corresponding text result. Like given this audio signal, then the function recognizes how are you. Okay, and for image recognition, the input signal may be an image, and the function just output the meaning of this image, that is cat. And we can also input the situation of a goal. Okay, and this function output the next move. Okay, we may also input for that dialogue system. We may also input what a user say, like hi, and then this function output hello. That is a system response. So for machine learning, we can imagine that we try to find good functions for some specific task, and this function may achieve the goal of this task. So conceptually, we can see a machine learning framework like this. We may construct a set of functions like F1, F2, and so on. And right now, if we want to do image recognition, we want to construct the function or select the function that when we input a cat image, then this function will output cat. When we input a dog image, then this function will output dog. Okay, and we may also construct another function like F2, and when we input this image, this function may output monkey. When we input this image, this function may output snake. And obviously, the function F1 is better than function F2. Okay, when we try to do image recognition. Okay, so how can we define what is a good model? Okay, so we need a lot of training data, and then we need to define the goodness of a function F. Okay, so how can we achieve that? We use the supervised learning. That means we need to collect a lot of training data, and then we need to also label it. Okay, like we collect these 3 images, and then we label the first image as monkey, the second image as cat, the third image as dog, and then we input these images and these labels to construct various functions. And we can also define the goodness of a function by whether the output of the function is close to the expected result. Therefore, for machine learning, we have several steps. The first step is we may construct a lot of functions, and given the training data, the step 2 is we need to measure the goodness of each function. And then step 3 is we pick the best function, f star. And this part is called the training part. Okay. And for the testing part, given a new image, and then we use this function will output the predicted result. So how can we do machine learning, or how can we do deep learning? Okay, we can divide it into 3 steps. Step 1 is we need to define a set of function. Step 2 is we need to measure the goodness of a function. Step 3 is we need to pick the best function. So let's go to step 1. In deep learning, the step 1, how can we construct a lot of functions? The method we do is we use neural network to construct this function set.
Before talking about the neural network, we need to understand the how our brain functions. Okay, and our brain consists of many neurons, and for each neuron, there are many connections with other neurons, and these neurons can be communicate with each other by the information transformation that may be in the representation of electrical form. Okay, and by transmit the information and do some process, and transmit to another neuron. Then through the communication and the complicated process of these neurons, we can have perception, we can have understanding, cognition, and so on. So we want to develop a mathematical model to mimic such communication between neurons. That is the origin of neural network. So the basic component of the neural network is neuron. And we can mathematically represent the process of a neuron by this equation. So we can assume that there are k inputs, A1, A2 to AK. Okay, and we may for each neuron we may have k different stimulus, and for each stimulus in each neuron we will linearly combine this stimulus and to get the response. Okay, and how we combine this stimulus, that is by the set of parameters, weighting parameter. Okay, so we will linear combine this stimulus, input stimulus, and then plus a bias. Okay, and this bias value may be the background information or side information of the of this neuron. Okay, so we will linearly combine them to get the output z value, and actually before output the value, we will also input the z value into an activation function, and usually the activation function is a nonlinear function. And finally, after this nonlinear function, we will output the value a. So this is the procedure of a neuron. So, for example, the stimulus value may be 2, -1, and 1, and the weight is 1, -2, and -1. And then by linearly combine them, we will get 2 multiply 1, -1 multiply -2, 1 minus 1 multiply -1, plus the bias value 1, and then we get the z value equal to 4. And then we can input the z value to an activation function. And usually in early years, one of the most popular activation function is the sigmoid function. This is an example of a sigmoid function. We can see that it's quite similar to a step function. Okay, that means when the z value is close to 0, then the output value would be 0.5. However, when z increase, then the output function quickly converge to the value 1. When z value decrease, then the output value will quickly converge to 0. Okay, and this is the mathematical formulation of the sigmoid function. And the sigmoid function is usually used as an activation function. So when we input 4, the output of the activation function would be 0.98, which is quite close to 1, because when we input 4, then the corresponding output value is quite close to 1. Okay, and in a neural network, we connect many neurons. Okay, and a different connection leads to different network structure. For this neuron, so we will connect a sequence of neurons, like the output of the first neuron would be this, the output of the second neuron would be this, and then the output of the neuron would be this. And then for the secondary neuron, it will collect all these inputs and do linear combination, and then output to the third layer neuron. Okay, so each neuron can have different values of weights and biases. Okay, so remember that the weight here may be totally different from the weight here, and also the bias value can be different. Okay, and the weight and the bias are network parameters. So how this neural network process the given input totally depends on the weight and the bias. Let's take a look of an example. So given a fully connected fifth wall network, that means any two neurons at different layers may be linked together. And when we have a two-dimensional input, one is 1, another one is -1. And if the weight is 1, -1, -2, and 1, the bias is 1 and 0, then the neuron of the first neuron of the first layer, by linearly combine them, we will get 1 plus 1 multiply 1 plus -1 multiply -2, and then plus 1, and then we get 4. And when we input the number 4 into the sigmoid function, we got 0.98. And if 1 multiply -1, -1 multiply 1, and plus 0, then the z value is -2. We input the -2 into the sigmoid function to get 0.12. And again, we pass this information to the second layer. So the input of the second layer would be 0.98 and 0.12. And then we can do the same process to get the output of the second layer. That is 0.86 and 0.11. And then we do the same process again. And then the final output would be 0.62 and then 0.83. So this is the whole process of a fully connected feed-forward neural network. Here is another example. When we input 0, 0, and after all this process, the final output will be 0, 51, and 0.85. So conceptually, when we give different input, we will give different output, and the whole neural network can be viewed as a function. So based on the two examples we have already mentioned, when we input the input vector is 1, -1, the output would be 0.62 and 0.83. When we input 0, 0, this case, okay, when we input 0, 0, the output will be 0.51 and 0.85. So this network can be viewed as a function, and given input vector, this function will output also a vector. So how can we define this function? Okay, so given parameters theta, we will define a function. Okay, we will define a function, and the parameter consists of the weighting matrix W and the bias B. So given network structure, actually, if we already define this network structure, we actually define a function set. Okay, because when we change the parameter, we will get different function. Okay, and with this network structure, we actually define a function set. Okay, and each function corresponding to a set of parameters. So theoretically, a neural network is look like this. We have an input layer, okay, and the input layer consists of the input vector that would be n-dimensional, and then we can connect to the input layer to several hidden layers. So we may have layer number 1, layer number 2, layer number 3 to layer number L, and the final layer is called the output layer. The output layer will output maybe m-dimensional output vector. Okay, that would be y1, y2 to ym. Okay, and actually this structure is exactly the same as the neural network that was proposed in almost maybe 30 or 40 years ago. Okay, this is just the same as the neural network proposed many years ago. So what's the difference between neural network and the deep learning? Actually, deep learning, deep means many hidden layer. Okay, so when we have many hidden layer, we say that it's a deep neural network. Okay, so you may imagine that, okay, this is a technology proposed many years ago. So why does the deep learning or the deep neural network emerge again in recent years? That is because right now we have more and more data, and right now we have a very powerful computational device like a GPU. So although this idea was proposed many years ago, but in early years we don't have so many data, and we are not able to construct a very deep neural network. At that time, we don't achieve good performance at that time. But however, in recent years, because of the development of big data and GPU, we are now able to construct and train a very promising neural network. So let's emphasize the output layer. Okay, the output layer, originally the output layer is that given the linear combination, the result of linear combination will be z, and then after the activation function, the output y1 is the result of the activation function. Okay, In general, the output value can be any numerical number. Okay, but these kinds of situation may not be easy to interpret. Okay, so many researchers like the output to be limited into the range from 0 to 1. Okay, in this case, we can use a softmax layer as the output layer. So what is the softmax layer? That is when after we get the linearly combination value, we take its exponential. Okay, we take its exponential. So if the z value is equal to 3, the exponential value may be 20. Okay, and we have another neuron. We get the value 2.7, and another one is 0.05. Okay, and we sum them together and divided this each value divided by the summation of all values. That is normalization. Okay, so finally we output the first value as 0.88, the second value 0.12, and the third value is approximately 0. Okay, so in this case, when we do these kinds of summarization, this kinds of normalization, we can output the value in the range from 0 to 1. Okay, and each value is between 0 and 1, and if we sum all of these values, we can get 1. So this is kinds of probability form. Okay, and this is the so-called softmax layer, and the softmax layer can be designed as a kind of output layer. So let's see a real example, like digit recognition. So we want to input a digit image, and then through the model, we want to recognize this is the digit 2. Okay, so how can we represent the input? So the input is an image. Okay, and then we can read the intensity value from left to right and top to bottom. And if this is a 16 by 16 image, then we have 256 intensity value. Therefore, we can construct a 256 dimensional input vector. So this is the input vector. Okay, and we want to construct a neural network that output the probability of each digit. Okay, assume that right now we have digit from 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have 10 different digits. And we want the output layer output the probability of the given image belonging to 1, the probability of the input image belonging to 2. Okay, so we want to output this probability vector. So in the output layer, each dimension represents the confidence of a digit. Okay, and in the best case, we want the probability of this image belonging to 2 is the highest. Okay, that should be much larger than any other probability. Okay, so what we need is we need to find the best function such that the output probability vector most match with the real situation of the input image. Okay, as we said before, when we define the structure of the neural network, we actually define a set of functions. And right now, we need to find the best function from them that can give us the most accurate result. Okay, so this is the formulation of a handwritten digit recognition. Okay, so this is the detail of the neural network. actually we define a function set, and this function set containing the candidate for handwritten digit recognition. Okay, and what you need to do is to decide the network structure and that the good function in your function set. Okay, so first you need to design your network structure, and the next you need to prepare the training data and the ground truth, and input this training data and ground truth to the network to find the best function. So right now you may ask, how many layers we should design, how many neurons in each layer. Okay, when you design the network structure, the answer is that depends on your application, depends on your goal. Okay, so the answer would be try and error, and plus some intuition or some domain knowledge. So based on your domain knowledge, and you need to try different network structure, and then you can maybe you after many trials you can find one of them is the best. Okay, so you may also ask another question: can the structure be automatically determined? The answer is yes. The most state-of-the-art research has been proposed that we may be able to automatically determine the structure. Okay. However, this is just the most recent result. Okay, and in many research opportunity are still remain to be discovered. So right now we have already finished introducing the step one, that is the neural network. And the second step is how can we determine the goodness of a function. So as we said before, when we design the network structure, we actually have already defined a set of functions. So how can we pick one of them as the best function? To measure the goodness of a function, we need to prepare the training data. The so-called training data are the images and the layer labels. If we take the handwritten digit recognition as an example. So the training data are images, just like this. So we collect a lot of training images. And the layer labels, that is the ground truth or the expect answer of the corresponding image. Like this should be the handwritten digit 5, and this would be the handwritten digit 0, and so on. So the learning target is defined on the training data. So we input the training images and the corresponding ground truth to the network, and then we would like to make the network accurately predict the label of a given image. So given the training image, we transform this image into the input vector, and then we input this vector into the neural network, and the neural network will output 10 probability value. Okay, so assume that the output layer is a softmax layer. The first output value corresponding to the probability of the given image represent the digit 1, and the second output value represent the probability of the image presenting the digit 2, and so on. So the learning target is when we input these kinds of image, the y1 value should be the largest. If we input these kinds of image, because it's a handwritten digit 2, then the y2 value should has the maximum number. Okay, so we would like to mathematically represent the goodness of a function. So the idea is we define a term called loss. Okay, a good function should make the loss of all example as small as possible. So given this image to the network, okay, and through the based on the parameters, this network define a set of functions, and we would like to find the best function such that when we input this image, then the best case would be the value of y1 is 1, the value of y2 and the value of y10 should be all equal to 0. So in this case, this network optimally predict the given image is the handwritten digit 1. Okay, and we want to make the output probability vector as close as possible to the ground truth output vector. Okay, loss can be the distance between the network output and the target. So we can define mathematically define the loss value. And right now we have many training data, so we can calculate the loss of each training data, each training image. So given this image, we can calculate the loss L1. Given this image, we can calculate the loss L2 and so on. And we want to make the whole neural network predict for any handwritten digit as best as possible. So we want to find the network parameter theta star that minimize total loss. The so-called total loss is we sum all L1, L2 to LR together. Okay, we want to make it as small as possible, such that we can find a function in the function set that minimizes the total loss. So this is how we define the goodness of a function. Now the most important problem is then how can we mathematically or systematically pick the best function? So right now we have already the network structure. We know how to measure the goodness of a function, and then the most important step is the training step. How can we pick the best function that really achieve our goals? So how to pick the best function? Okay, one possible way is enumerate all possible value. Okay, if we thoroughly or exhaustively test all possible parameters, so what kinds of situation would happen? Because right now we may have many layers, okay, and at each layer we have many weighting and the bias, okay, and just imagine that if there is a layer L and the layer L plus 1, and if there are 1,000 neurons in each layer, then there are the 10 power 6 weights just between these two layers. And you can imagine that if you have many layers, how many parameters you should enumerate. So it is impossible to enumerate all possible value, okay, in a neural network. Okay, and for example, in speech recognition task, they usually use 8 layers and 1,000 neurons at each layer. So there are millions of parameters. So it's impossible to exhaustively check all parameters. Then how can we do that? A systematic way to find the best parameter is to use the gradient descent algorithm. Okay, and this algorithm is actually one of the most important algorithms in the optimization theory, and we will offer another class about specific to optimization theory. So if you are interested in optimization, please take the optimization class. But the idea is like this. Assume that this is some specific parameter W, okay, and this curve is the total loss, okay, assume we only have one parameter, and this is the loss curve. Okay, so how can we find the best W such that we have the minima total loss, that is this value. Okay, so initially we pick an initial value for W. We just randomly pick one. Okay. By the way, prior to gradient descent, in early years, we may use random selection or using RBM pre-train. Okay, so to pick the initial value, we can just randomly pick one, or use the RBM restrict Boltzmann machine to do pre-train or to initialize the initial parameters. Okay, but usually we randomly select it is good enough. Okay, so first we randomly pick a W, and then we compute the partial derivative of the loss function, the partial derivative of the loss function to the parameter W. So you can imagine that you just stand at this location and see the partial derivative. If the partial derivative is negative, that means we need to increase W, just like this case. At this position, this is the direction of the partial derivative, and the sign of the partial derivative is negative. So we need to increase the parameter W. Otherwise, if the partial derivative is positive, then we need to decrease the W. So at this point, we know we need to increase W. To what degree? Okay. In this case, we update the W by this formulation. Okay. W is updated to W minus eta partial derivative, where eta is called the learning rate. Okay. And because this is a negative value and the eta is a positive value, so let's actually increase W. Therefore, we move the direction toward the right. So we may move toward here, and then the next W is here. So this is a newer W. This is old W. Okay, so we move from this point to this point. That means we update the W from this one to this one. And at this point, we keep repeating the same procedure. Again, we calculate the partial derivative and check its sign. And then we will find that we should also increase W again. And then we move to this position. Okay. So we repeat the same procedure until the partial derivative is approximately small. Okay. Or when the update is little. Okay. That often happens when we move to the point at the local minimum. So mathematically, we have many parameters, and for each parameter, we can calculate the partial derivative and then move to the direction, to appropriate direction. Okay, so we may at the first we will initialize the W1 as 0.2, and then we update it to 0.15. Initially, we have the W2 as minus 0.1, and then we update it into 0.05, and so on. And actually, all partial derivative can be combined together to be a matrix. So this is the loss function. Take the partial derivative of the loss function to W1, and this is to W2, and so on. And this is the so-called gradient. And we can repeat this process again and again. So we update W1 again and again, and so on. So finally, theoretically, we will find the minimum loss. We will find the set of parameters that minimize the loss function. So this is an example when we have two parameters, W1 and W2. And this is a plane, different color represent the value of the loss function. Okay, so you can imagine that this is a valley. Okay, at the center, there is a valley at the center, and when we go in from the center to the outside, the height of the loss function, the value of the loss function increase. So increase. Okay, so initially we may randomly pick a starting point, maybe like here. Okay, and for example, when we set W1 as this value and the W2 as this value, then the loss value will be 9. When we set the W1 as this value and the W2 as this value, then the loss function, the loss value will be 1.5. Okay, so how can we find the best set of W1 and W2? We initially pick a starting point, and then we compute the partial derivative to W1 and W2 and find the best direction to move, and then we move to a new point. Okay, and this direction is determined by the partial derivative, and the length of moving is determined by the learning rate. And then at this point, we again check the partial derivative and determine the best direction to move. And then we move to here and then move to here. So finally, we can find the minimum. Hopefully, we will reach a minimum. Okay, so everything looks simple, right? By using gradient descent, we can find the minimum. However, the loss function is usually very complex. Okay, and actually the gradient descent algorithm never guarantee global minima. So when we start from different initial point, we may reach different minima. So we will get different result. Okay, just like this example, if the the surface of the loss function is compressed like this, then if we initially start from this point, then we will find a minimum at this point. And if we initially start from this point, and then we will find a minimum at this. And actually, this point is really the global minimum. So it's difficult to really find the optimal, the global minimum. Okay, and there are some tips to help you avoid local minima, but no guarantee. You may also imagine that the problem looks quite simple when you know the surface of the loss function. It is for us. It is quite easy to find the position of the global minima, just like we can see here. When we see this loss function, we can easily know that this is the global minima. So the corresponding W is here. However, when you do neural network training, it's not like you can know the overall loss function at the beginning of your training. It's more like you are playing Age of Empire. Okay, if you ever play this game, you know that initially you just have a very short vision. Okay, you just can realize a local neighborhood, and then when you move, you can discover a new region. Okay, so you cannot see the whole map initially. Okay, you just try to move to different direction and to see a very small portion at every time you move. Okay, so you don't know the whole picture. You don't know the overall loss surface. Okay, so this is the difficult part, and you don't have to worry about how to implement the gradient descent algorithm, because that is the most kernel part. Okay, But right now we have many open library that can for us to do gradient descent or the so-called backpropagation algorithm. So we can use backpropagation algorithm to efficiently compute the partial derivative. And right now, there are many tools we can use, like TensorFlow that was proposed by Google, and Torch, Ciano, or LibDNN, developed by a student in National Taiwan University. Or another very famous tool is called Cafe, or Microsoft CNTK, Channel, or MSNet. Okay, so don't worry about the partial derivative. The toolkit will handle it.